Welcome to the class of Intelligent Product Design. We are inside the selection of sensor, and in the last class we have mostly focused on positional sensors, and these positional sensors were generally based on non-optical sensing technique, except one or two like the Sanak effect based ring laser, gyros, etc. Now today I will talk about mostly the optical sensors, and the very figure here is actually showing one such laser based sensing system. Now it can be laser based, it can be LED LDR based, there are many different possibilities with optical sensors, but the fundamental idea is same, that you are sending an optical signal and the signal is reflecting back, and from that reflection you are trying to figure out that how far away, what is the position, and similar informations of the system. And in these directions LEDs are possibly one of the cheapest ways. However, for selection of LED you need to also know a couple of points. For example, you choose a blue LED, it would not mean that it would sense blue LED, but it would mean that it will actually send the blue light, but it will sense the red and the green. Okay? Or also the ideas are required to know where to place the emitter and where to place the receivers. So there are many variations of it, like there is a opposed mode 1, there is a retroreflective mode, and there is a proximity mode. Proximity mode also can be of two types, divergent and convergent. So we can have a look at each one of these systems, so one by one. So let us look into the opposed mode, figure A very clearly. In the opposed mode, what is happening is that you have an emitter here, okay, and you have a receiver just in the opposite. Now the object is coming like this. So at a certain point when the object is starting to infringe, the receiver will not receive the light. So that way the receiver will understand the position of the object, okay, and then it will take some action. So this is also known as a direct scanning or a beam break technique or a through beam mode. One of the examples where you might have seen that this is used is in airport. When you actually receive the luggage in the luggage belt, you will see that there is a conveyor belt like this, which is continuously rotating in one direction, and from the top slightly from a height the luggages are coming. Okay. Now some luggages are already rotating here on the conveyor belt, and some luggages are coming and meeting this here. The problem is that if there is a luggage already here, then there will be a collision between two luggage and both of them will get damaged. So they use this kind of a opposed mode sensing, which actually senses. So let us say you have two sensors here, okay. As the luggage comes here, then it senses that the luggage is approaching, then it immediately stops this particular belt and it allows this whole thing to move fast. So and here also in the same way, between the two position, here also you would see wherever the chute is, just before that or just after that, just before, just after, you are going to have a similar kind of a opposed mode sensing technique. So this is something which is used very much in terms of the position of a system. Now in some cases, instead of having a transmitter and receiver, there may be a problem in terms of having too much of electronics in the system. Then what one can do is simply put a retro reflector here. So this is called retro reflective layer. So what happens is that in this case the light goes and reflects back. Of course, part of the light will reflect back, and that is the part that you have to sense. So that is the retro reflective mode sensing system. So this is the configuration of a retro. Okay. So in this case, for example, emitter and receiver creates an angle with respect to the mirrored surface, but if you have this type of a situation, okay, that is emitted and received beams will become parallel. So, we will look for that type of retroreflective reflectors through usually a matrix of tiny corner cube prisms, so that you get the beams parallel. Okay, these retroreflective reflectors are used also sometimes in terms of the highway markers. Okay, so that the vehicle light goes, hits and comes back, and through the way the vehicle actually understands its position. So, something which is very common system. Now, then there can be other type which is called the proximity and the divergent mode. Okay. So, what does it do here? Well, this photoelectric or ultrasonic, both of them can be used in this case, either photoelectric light based or ultrasonic sound based. Proximity sensing detects an object directly in front of the sensor by deflecting the sensor's own transmitted energy reflected back from the object surface. So, earlier system that I told you, it gets the energy reflected from the retroreflector. In this case, it takes the direct reflection from the object itself that reflects back. Now, once the signal hits the object, it can either create a divergence like this, okay, or it can also, you can also create a situation where the light is focused to a point and then you get a convergent beam sensing. So, in diffused mode, the emitted light strikes the surface of an object at some arbitrary angle. The light diffuses at many angles and some small portion of which reaches the receiver. But this is relatively inefficient, and maybe the better technique is to use a convergent beam sensing, where actually it gets focused and then gets reflected from the object and goes back. So, you get lot of reflections from the system. Now, with the exception of the infrared layers, LEDs generally produce less light. Okay. So, that LED reflection that you get back generally is pretty weak, and hence instead of directly measuring the intensity, many times we actually depend on the modulation of the sensor's light beam. Now, LEDs can be turned on or off at a high rate of speed. Okay. So, you need not send the LED light as a continuous light, you can keep it as a pulsating light. So, you can see the pulse here, okay, continuous on off system. Now, this on off system, that can be actually modulated, and then from that modulation, the change of the nature of modulation can help you in terms of detection of the object. Okay. So, that way, even if the intensity is less, but the pattern of modulation, that on off signal pattern that you are receiving, will actually tell you about the nature of the object or the position of the object. So, you can depend on it. Now, this is one way that you send a type of a modulated signal, which can be of several kilohertz frequency. Another way is that we utilize something which is very much used to be used earlier days in picture tubes, but today a semiconductor version of it is also there. So, it is called a photomultiplier tube or PMT. Now, what does the PMT does? It actually kind of increases the photon density, sometimes up to the level of 100 million times. So, wonder that it is used in low light level spectroscopy, things like confocal microscopy, Raman spectroscopy, fluorescent spectroscopy, nuclear and particle physics, astronomical, and the medical diagnostics. Now, how does a PMT photomultiplier works? Well, it has a high energy photon that is coming to the scintillator, which is the having ionization track. From there, there is a primary electron that is allowed, okay, and there is a focusing electrode that is there. So, it focuses it to one part of the reflector only, and this generates the secondary photons, and then you see there are two of them, then this generates more numbers, then this generates much more numbers. By the time each one of them is going, the number is increasing and you get many of them. So, by arranging these kind of what we call the dinodes, you can actually multiply the secondary electrons in the system, and that way it can work like a photo multiplier. This is the technology that easier to explain through this kind of a PMT, but this is something that is used routinely for any system where the light that comes back is very low. So, in such cases you need to have this kind of a multiplier technology. Now, another important thing is that many of these sensors, we try to figure out that whether we have to use an analog sensor or a digital sensor or a digital transducer. Now, the digital transducer, the difference between analog and digital is that analog gives you a continuous signal, whereas the digital applies sampling. So, that means suppose I have a signal like this, and digital may actually take each one of these points, not this entire signal, but each one of these points. So, this is the way the digital signal reaches. Now, however, this also creates a quantization error, because if the sampling point is high enough, let us say you have to pick up all these the continuous wave pattern, and if you would have chosen only 3 points here, 1, 2 and 3, it will only show that there is no intensity at all. So, if you have at least 5 of them, then it shows a digital signal which works like this. You get at least some periodicity, but still that would not reveal the true picture. If you get more number in between these, then you can gradually build up that no, it is not a linear variation, it is a nonlinear variation, and similar like that. Okay. So, that is the quantization error that is you have to avoid with the help of the sampling points. So, these are the certain points that you need to keep in your mind from the analog to digital conversion of a signal. Now, we come to the motion sensing transduction. So, our discussion will be limited primarily to motion transducers and corresponding to the digital counterpart of it. Now, by using a suitable auxiliary front end sensor, other measures such as force, torque, temperature and pressure may be also converted into motion and subsequently measured using a motion transducer. For example, altitude or pressure in aerospace applications, these are obtained using a pressure sensing front end, a bellow or a diaphragm, okay, in conjunction with an optical encoder to measure the resulting displacement. So, we essentially we are going to sense the motion, but in order to sense it, we can use force or such a thing, any such thing like torque or temperature as an interrogating medium. Remember that we have talked about a 2-port and a 3-port system. So, these are the systems which are like 3-port systems, and through that you can measure the motion in a system. Now, what are the advantages? Well, the digital signals with this 3-port are less susceptible to noise and disturbances. So, they are robust. Complex signal processing with high accuracy and speed is possible, particularly because you can directly sort of analyze the signal with the help of a digital computer. Both of them are working in a digital environment. High reliability, minimizing the hardware costs, large amount of data storage using compact high density data storage methods that is possible. You are only keeping some sampling point data, not the full data. Fast data transmission and use of low voltage and low power, and typically that is why they are of low cost system. Now, since these digital systems are so good, we can also see another particular application of this digital sensor, which is in the form of encoders. So, this is also known as shaft encoder, and these are digital transducers which are used for measuring angular displacement and angular velocities. And they have a wide range of applications in terms of control of robotic manipulators, machine tools, industrial processes, digital data storage device, positioning tables, satellite mirror positioning system, rotating machineries. There are huge application of the encoders today. How does an encoder work? Well, in this case, what you are doing is that you are creating a kind of a pulse generator, okay, and how you are going to do it? So, you are rotating a wheel like this, okay, and let us say that you are only allowing the current here at this location, okay. So, suppose you are having a current source coming like this, okay. Now, when this position is here, then it is opaque, which means it is 0, no current. Only when this slot is coming, then the current, the light can emit. So, the optical system, LED or whatever, can actually emit the light. So, the light goes and it creates a spark. So, that is a pulse generator. So, you get a continuous pulse depending on the rotational speed of the wheel, okay. So, that means if the wheel is rotating at a low speed, you get like this, and if the wheel is rotating at a high speed, this is a natural way of sampling. If the wheel is rotating at a high speed, you get much more dense pulses, okay. So, this is by actually measuring this change in the pulse frequency, you can actually measure what is the wheel speed omega. So, this is for angular velocity, and then similarly for angular acceleration. Now, you can do this through optical encoder. You need not have only one slot, you can have many such slots. So, you can have incremental and absolute optical encoders based on this technology, and again it is a rotating disc on a shaft. The principle is very much similar, only thing is that you have many light sources coming up from the top, and the sensors are picking it up, and then either you measure the incremental changes that is happening in the system, or you measure the absolute values of the system. So, the pattern changes based on it. So, you can have 4 techniques on it: optical photosensor, you can have a sliding contact electrical conducting one, you can have a magnetic saturation, and a proximity sensing method for this type of encoders. So, let us look at the incremental encoder. Okay. If you only look at one part of an incremental encoder, just one level of these arrays that is there, okay, we can call these pick off points 1, 2s, etc. And then you can have basically you can measure, for example, that from this pulse to this pulse, what is this degree that shifting that has happened, and at different angular velocities you expect these to come up at a particular rate, which you already know that at which rate it is the next point is going to come. So, depending on that frequency, this change is going to happen, and from that you can actually measure that the angle is essentially the number of pulses that you are measuring, the maximum number of pulses that is possible, and the theta max, the range of the angle between the two. So, you get theta, and similarly you can also get the angular velocity of the system. So, that is for an incremental encoder system. For absolute encoder, is a little bit different. In this case, it is not the increment from point A to B, but actually you have such concentric circles, okay, and some circles have a pattern of actually blocking the light different. Like this one is blocking all throughout, this one is blocking two in between slot it is open. So, if you can measure the light in such a system, you can figure out that what is the absolute angular change that has taken place in the system, and then that data you can actually represent in terms of a binary code. Now, the ranges differ between incremental systems, particularly between, first of all, let us say the angular systems. The incremental is 2 pi, 18,000 lines per 2 pi is the resolution, temperature is 80. Okay. And the absolute angular system can be measured in terms of the bits, the number of bits of the system, and it works also up to 80 degree centigrade temperature. The incremental linear systems works for a slightly higher, and their scanning line for incremental linear is 80 lines per millimeter, and whereas for absolute linear it can measure an absolute distance of 1 micrometer. That is the minimum size that it can do, for certain varieties of optical encoder system. So, depending on your demand of resolution or your demand of range, you can choose a particular type of an encoder. Now, the other varieties that are used is in terms of photoelectric receivers like photodiodes, which are generally reserved for applications that require extremely fast response time of linear response. It's basically based on the PN junctions, and then photocell, which is used whenever greater sensitivity to visible wavelength is required, and phototransistors, which is most widely used to receive the optoelement in industrial photoelectric sensor design, because they offer a trade-off between the light sensitivity and response speed compared to photoresistive and other photojunction devices. So, for a given level of source voltage, what you can see is that the collector current is nearly proportional to the intensity of light falling on the collector base junction, and hence this can be used as a measure of the light intensity. And these are the semiconductor versions. So, either it is photoresistors are based on cadmium sulfide, photodiodes are based on silicon or germanium, or phototransistors are basically NPN junctions, and they are just the other counterparts we have earlier discussed. They are the semiconductor counterpart of these sensors. One of the case in which this is regularly almost used, again a system for say the displacement measurement, is called the charge coupled device or CCD. It is essentially an integrated circuit using these elements of semiconductor, like a silicon wafer p type or n type is oxidized, and then matrix of metal electrode is deposited on the oxide layer. So, you can see that the matrix of the silicon wafer on the silicon substrate is actually silicon dioxide layer is given, and on top of it the electrodes are created. So, when light falls into the CCD element from an object, charge packets are getting generated on the system. Now, if an external potential is applied to a particular electrode of the CCD, a potential well is formed under the electrode and the charge packet is deposited here. This charge packet then can be moved across the CCD to an output circuit by sequentially energizing the electrodes using pulses of external voltage. So, such each charge packet will correspond to typically a pixel. So, you can actually measure pixel by pixel as the charges are coming to you. Another last type of a system that I will tell you is used very extensively is the optical fiber. Now, optical fiber you generally utilize it for the communication of signals, but for the sensing optical fibers are also equally useful. So, These fibers can be made from drawing the glass fibers or similar polymers which are of the size of human hair, and they can transmit the light on the basis of the principle of total internal reflections. So, how would such a system work? Well, as you can see here that there is a electrical pulse in, and that is changing it to light, electricity to light. Then there is this total internal reflection happening inside the optical fiber, and then there is a light to electrical conversion. Then you are getting the electrical pulse out of the system. Now, this you can get it from a glass optical fiber or a plastic optical fiber. We call it GOF or POF. Now, these optical fibers can be of different types. One is a single mode fiber, that means it allows single path through the fiber, and another is called a multi-mode fiber, so that multiple paths are possible through the fiber. So, generally single mode fiber is 9 by 125, that means the core to the cladding diameter. So, this is the core you have, and then you have the cladding. The cladding and core together, their refractive index are matched in such a manner that the total internal reflection is possible. So, the ratio is 9 micron to 125 micron, and that is for the single mode fibers. Now, the multi-mode fibers, they are actually cable core is much bigger, 850 or 1300 nanometer, and the core diameters are 50, 62.5 and 100 micrometers. So, there are different types of cores that allows different types of modes passing through the system. So, if I try to compare between a GOF system, the glass optical fiber, and a plastic optical fiber, we can see that first of all, optical fibers are not good in the ultraviolet range. Visible light range, yes, they are good, and infrared range also they work, but the plastic fiber, their performance decreases in this region. Beyond this 900 nanometer region, the plastic fiber's performance drops down, where the glass fiber can work even up to the infrared LEDs. So, starting from the red LED to infrared LEDs, and the visible light spectrum also, particularly this region, you will get a glass fiber. So, the glass fiber has a much wider range in comparison to the plastic fiber. But plastic fibers have other advantages, like you can actually flex them. Glass fibers would break, but plastics would not. So, you can actually use it for applications where there is a mechanical strain present in the system, and also they are cheaper, and there are particular bands where they work all right, like visible red LED. They work all right, and generally the sheeting materials are also less expensive, like polypropylene, Teflon and nylon. They are used to shield the plastic fiber optical assemblies. Now, of course, when an optical fiber is subjected to perturbations of different kind, like a geometric change or an optical change, then the nature of the wave that you are getting from the receiving end, from the transmitting to the receiving end, will change. The intensity will change, the modulation will change. So, that can be used to measure the external influence. So, in this case, you can have an auxiliary system that can use this change, that can create a disturbance, and by measuring the changes in the optical fiber, you can actually try to measure the changes that the interrogation is actually creating. That way, optical fibers can be used as temperature, stress, strain, rotation, electric and magnetic currents, many such things, wherever you can change the environment. Like you can see here, there is a light source, there is a light detector, there is the environment here. If the environment gets changed, then the detector will detect the change in terms of the modulation or the intensity of the light. So, that is the technology by which you can do it. In fact, in some cases we use something more also. We can also use a small micro bends in the system, and if there is a pressure that pressure will change the nature of the microvane, and that will also change the path of the light. So, thus you can use optical fibers in a variety of ways in terms of sensing that if there is a change in the environmental condition. Thank you.